Something about this object refuses to settle down. Even now, long after it should have faded into the background, 3I Atlas keeps doing things that force astronomers to look twice. Every new observation adds another complication. Every explanation seems to create two more questions. That's not how comet stories usually go. Normally, once an object passes perihelion and starts moving away from the sun, interest drops off quickly. Activity fades. The physics becomes predictable. The story ends quietly. But 3I Atlas never gave us that ending. Before we go any further, let's correct one common claim. 3I Atlas has not left the solar system. Despite how often that gets repeated, it simply isn't true. The object won't reach Jupiter's Hill radius, its closest meaningful gravitational interaction with Jupiter, until sometime in March. And it will remain inside the solar system throughout all of 2026. If it stays bright enough, large telescopes could continue tracking it well into next summer. That alone is unusual, because by this stage, a normal comet should be running out of energy. Instead of fading, 3I Atlas is becoming more organized. Instead of losing structure, it's developing sharper features. And instead of behaving like every other comet we've studied, it continues to act like something entirely different. The clearest example of this is its anti-tail. Most comets produce two main tails, a dust tail and an ion tail, both pushed away from the sun by radiation pressure and the solar wind. Some comets also show an anti-tail, which appears to point toward the sun due to geometry and particle motion. But those anti-tails are usually weak, short-lived, and much smaller than the main tails. That is not the case here. The anti-tail of 3I Atlas is not a minor feature. It is the dominant structure. Brighter, longer, and more sharply defined than the main tail. That alone would be rare. What makes it truly unsettling is how it behaves. Let's jump to the latest Hubble observations. On December 27, Hubble recorded a 172-second exposure of 3I Atlas using the WFC3 UVIS instrument at a wavelength of 0.5851 microns. The raw image looks ordinary, flat, quiet, nothing dramatic. That's expected. Raw images often hide the most important details. Once the data was processed using a Larsen-Cecchinina rotational gradient filter, however, everything changed. A clear double-jet structure appeared. Now compare that image to a similar one taken just 15 days earlier, on December 12th. The difference is obvious. The brightness of the two jets shifts dramatically in a very short time. One jet brightens, while the other fades. Their shapes change. Their orientation subtly shifts. But the most important detail is also the most troubling. The brightest jet points toward the sun, not away from it, toward it. This is not an illusion. It is not a trick of perspective. It is a real, sustained jet moving directly into the solar wind. No confirmed natural comet has ever shown behavior like this. What makes this even harder to explain is that it didn't start recently. Hubble observed a strong sunward jet as far back as July 21st, 2025, well before perihelion. That jet was extremely narrow and elongated, roughly 10 times longer than it was wide. It also showed a wobble of about 7 degrees. That wobble matters. It tells us the jet's source lies very close to the object's rotational pole near one end of the nucleus. Now here's where things stop lining up. After perihelion, 3I Atlas should have experienced a gravitational deflection of about 16 degrees. If its rotational axis stayed the same, the region that originally faced the sun should now be facing away from it, which means the original sunward jet should be gone. But instead of disappearing, something stranger happened. The original jet direction now matches the weaker jet seen in December. Meanwhile, A new and stronger sunward jet appears from the opposite side of the nucleus. The object now looks like a flipped version of itself. That should not happen if this were a passive, naturally sublimating body. So, how do we explain it? One possibility is that the jets originate from opposite sides of the nucleus. That would mean the object's behavior fundamentally changed after perihelion. For a natural comet, this would require heat to travel efficiently from the day side to the night side, activating a second jet. But heat conduction through comet material is weak and slow. It does not produce narrow, sustained jets aimed straight at the sun. That explanation struggles to hold together. In a technological context, however, the picture changes. A sunward jet could serve as shielding, deflecting charged particles, solar wind, or coronal mass ejections. A secondary jet could provide stability or protection along the object's path. And that brings us to another important detail. The anti-tail of 3I Atlas is not very transparent. It reflects a large amount of light and is noticeably harder to see through than typical cometary dust. That suggests dense material, not a loose cloud of fine grains, which leads to the second possible explanation. In this model, both jets originate from the sun-facing side of the nucleus, but consist of different particle sizes. Larger particles, around 10 microns, form the massive anti-tail. These particles can resist the solar wind for long distances, allowing the anti-tail to stretch hundreds of millions of kilometers. Smaller particles are pushed away quickly by radiation pressure, forming a weaker jet in the opposite direction. Gas particles would behave in a similar way. On paper, this explanation works. But there's a problem. We've never seen anything like this before, not once. The only way to decide between these explanations is through spectroscopy. By measuring particle speeds in both jets using telescopes like Keck or the Very Large Telescope, scientists can determine how the material is being launched. If the particles are leaving the nucleus at speeds greater than 1 kilometer per second, natural outgassing can't explain it. Solar heating alone tops out at around 500 meters per second. Anything faster implies an additional energy source. There's another clue hidden in the timing. Between December 12th and December 27th, the jets change dramatically. That's a very short time for such large structural changes. This points to either rotational wobble or extreme variability in the jet sources. Early signs favor rotational wobble because as one jet brightens, the other fades in a repeating pattern. This matches earlier observations. Back in July 2025, 3I Atlas showed a regular brightness cycle with a period of about 16 hours. It brightened and dimmed as it rotated. As mass continues to be lost, that rotation period may have changed, possibly down to around 15.5 hours or less. Avi Loeb's team is currently analyzing the new Hubble data to see if the rotation rate has shifted. Now, let's talk about the dust. The particles forming the anti-tail appear to be about 10 microns in size, much larger than typical comet dust. Particles this large can push against the solar wind, but only for a limited time. How far they travel tells us how big they can be. Each particle has a mass of roughly 10 to the minus 8 grams. Individually tiny, but together they reflect an enormous amount of light. By measuring that reflected light, scientists can estimate how much brightness comes from the dust versus the nucleus. Using this method, Avi Loeb estimates a minimum nucleus diameter of about 2 kilometers, assuming all observed light is reflected sunlight. If the nucleus produces its own light, then the dust could act as a reflective shield, hiding a smaller core. In that case, the nucleus might be closer to 1.4 kilometers in diameter. Either way, these are minimum values, and the dust cloud itself is close to opaque. A high-resolution camera wouldn't see a solid surface. It would see a glowing cloud. 3-eye atlas is hiding whatever lies at its center. So what does all of this mean? It means this object is not finished surprising us. Even as it moves outward, its behavior keeps evolving. The anti-tail dominates, the jets shift, the brightness changes, the color changes, and we need to keep watching it for as long as we can. Because one thing is clear, this is not behaving like a normal comet. Is it natural? It could be. But calling it probably natural feels less convincing with every new observation. The trajectory alone would be extremely useful for a probe moving through the solar system, or for an object designed to interact with multiple planets and moons. Could all of this be coincidence? Yes. But coincidence becomes harder to believe when anomaly after anomaly piles up. The long-lived sunward jet, the focused structure, the massive anti-tail fighting the solar wind, the continued activity long after perihelion. None of this feels ordinary, and yet very few scientists are willing to consider a technological explanation. We often ask where extraterrestrial civilizations are. Maybe the better question is why we ignore the possibility when evidence doesn't fit our expectations. If even a small fraction of unexplained phenomena are artificial, then the so-called Fermi paradox disappears. Perhaps they don't contact us because we aren't important. Perhaps they communicate in ways we don't understand. Or perhaps the universe really is a dark forest where silence is survival. If that's true, then broadcasting our presence for over a century may not have been wise. I hope that isn't the case. I appreciate you listening, Dot. There will be more data soon. There will be more observations. Furthermore, 3-eye atlas will keep challenging our preconceived notions. Dot, until then, remain inquisitive.